about this. So I thought what I would do first is run you all through an example. Diamond, can you see my, if I share my, are you at a computer?
I am, yes.
Okay. So I'm going to share my screen and I will run through just a basic example of logistic. Let me close all this stuff I have open. So many things now that our entire lives are on our computers, right? I mean, they were before, but now they really are. You guys are my last of 5 straight Zoom calls.
That's better than yesterday.
Yesterday was long. Okay, so you can see this data set. This is not a data set that you have. It's just a generic data set on diabetes. And so with this particular data set, I have a variable here that's poorly named called Y binary, and I'm actually going to change it to risk of diabetes. So Rick has diabetes, risk of diabetes. So we have a data set here that has some values for people's risk of diabetes. And what we want to do is determine what the predictors of that risk of developing diabetes is for people. So if you imagine a physician or a healthcare provider sitting with a patient and attempting to look at like what their risk of diabetes is, they would take into consideration their age and their gender and their cholesterol and their BMI and things like that, and their glucose levels to maybe try to do an intervention before they become diabetic. And so that's sort of what this data has here. And so you can see we've got a risk of diabetes score, which is divided into low and high, and then I've got their age and I've got their gender, which I recoded because I don't like it being 1s and 2s. Their BMI, I have their systolic blood pressure, their total cholesterol, I have parts of their cholesterol, and then I have their glucose, and you can ignore, I can get rid of this column here. And so to run a logistic regression, the very first thing that you do is the very first thing that you do with any data set, which is do your distribution and let's look at my risk of diabetes, let's look at my age, let's look at my gender, and we'll consider BMI, total cholesterol, and glucose. I'm recording this, by the way, so I'll send it to you guys and you can go back through. And I'm just going to press OK. So this is just data investigation, right? This is what we do with all of our data sets that we get to have an idea of, okay, I have 442 rows. Let's see, I have 440. I don't have any missing data, so that's good. It looks like the majority of the people in this data set are at low risk of diabetes. So 73% of people here are low risk for diabetes. And that's our basic understanding of the risk of diabetes right now. And our research question is, are any of these variables, age, gender, BMI, total cholesterol, and glucose, are they going to get me a better prediction of a risk of diabetes than simply just saying, oh, you have a 27% risk? Does that make sense?
Yes. Yes.
Okay, so it's a very similar setup to when we were looking at mean values, where we would say, okay, the mean total cholesterol is 189. And until I know other information, if somebody says, what do you think my total cholesterol is? I would say, well, I'd have to guess 189, right? The mean is our best guess for a continuous measure without other information, and the proportion is our best guess for categorical without other information. So I've looked at this data. I have sort of an understanding that I'm, 53% male. They're about 50 years of age. Our BMI is 26. That's just into the, that's the obese category. We've got, pretty decent range of cholesterol, and then we have our glucose measures. So my next question, and this goes specifically to one of you had this question about unadjusted versus adjusted analyses, and what does that mean? So we just did univariate analyses where we took a single or one or uni variable and looked at its distribution. That is a univariate analysis. Our bivariate analyses, or our fit y by x analyses, those are unadjusted analyses, unadjusted bivariate analyses. We're not adjusting for any other characteristics. We are simply looking at a single x versus a single y. So that's what the term is meant by unadjusted analysis. So to do that, I would go into fit y by x, and I'll put my risk of diabetes here, and I'll look at gender, because this is the only categorical bivariate that I have, right? This is my only contingency table one. So it's just gender and risk. Press OK, and I get what we've seen before, which is our contingency table. Unadjusted, this tells me that gender does not predict a risk of diabetes in this data, wherever this fake population is from. This is sample data in JMP. You have access to this if you want to go look up the diabetes.jmp in your sample data. And so our null hypothesis here is that there's no association between gender and risk of diabetes. And then we look at our p-value, and it tells us that we would stay with our null, that this 30% female are high risk, 25% male are high risk, but that's not a statistically significant difference. This is an unadjusted analysis. We've only looked at two variables. Does that make sense?
Yes, it does.
Okay. So we can also go ahead and look at our unadjusted relationships between risk of diabetes and our continuous variables. I find when I'm looking at unadjusted analyses between a categorical outcome and a continuous predictor, that it's actually easier to look at it in the reverse in our fit y by x. So if I put my categories in my x, I can then look at my mean ages, my mean BMI, my mean total cholesterol, and my mean glucose. So this is not a formal analysis. This is for me to get an idea of what the relationship is between diabetes risk and these continuous measures. So I can just press OK here, and we get the group means that you've seen before. And if I look at my means and standard deviations, and I can ask it for a t-test, and I can say, okay, so for my knowledge, it looks like we have a lower age. So right here, the people in the low risk category are about 4 years younger than the people in the high risk category. So this is something that you keep track of. You just want to have an idea of what this relationship is before we go into a model. And I find that doing it this way makes it easier to then interpret the logistic model, because you're expecting that there is a relationship now between age and diabetes risk. I can see that I've got people who are in the low risk category that on average are younger than those in the high risk category. Does that make sense?
Yes.
Okay. So then I can go through and I can look at BMI. Not surprisingly, we're lower. Those that are lower risk have a lower mean BMI. That's not a shock either. Then we're going to look at total cholesterol. And again, we're seeing that those in the low risk category have a lower mean total cholesterol. And we're also seeing here that those in the low category have a lower glucose, which isn't shocking, right? In what we know about diabetes, the people who are at lower risk should have a lower glucose score. Not everybody. Obviously, we have people with higher glucose scores here. So it's not like a complete discriminant. But on average, we're seeing lower glucose scores in the low risk category. So these, again, are unadjusted analyses. These, again, are telling us what our anticipated relationship between the risk of diabetes and our continuous covariates would be. So now I know I have an expectation that there's not a gender difference, but that these other 4 variables are related to the risk category for diabetes. So the question is if I put them all in a model together, does that give me a better prediction of the risk of diabetes than looking at them alone, right? Because if you had an overweight white male with a high total cholesterol and a high glucose walk into your office, you wouldn't simply say, oh, well, you're a man, here's your risk, right? You're not going to ignore all those other variables that you could find out. So you want to kind of look at them all together, and that's the purpose of modeling. And so in that case, we move into our adjusted analyses. So we're adjusting for multiple factors. Unadjusted is simply one factor. It's a single X, single Y. But now we want to adjust for multiple factors. And that's where we get into fit model. And so my risk is my outcome. And you'll see here it's a nominal logistic because there's only two categories. So there's no like low, medium, high, it's just lower, high. It's only two categories, so it can be nominal, logistic, doesn't matter. And now I want to put my age. I'm going to put gender in just to see if in the presence of other variables, gender now accounts for something else, but it might not. I don't have the expectation of gender being useful. I saw that in my unadjusted, but I'm going to stick it in here just to make sure. Let me throw in my BMI and my total cholesterol and my glucose. So my null hypothesis here is that my best predictor of the likelihood of somebody being at risk for diabetes is simply that, if I go back here real quick, without the model, my null hypothesis is telling me that somebody being in the low risk category is a 72.6% chance. Now I'm asking, is this model useful? So my null hypothesis is that it's not useful, that my best guess of whether or not you're at risk for diabetes is based on this information alone over here. My alternative would be that this model provides me better information. Does that make sense?
I kind of get thrown off there, so say that part again.
Okay.
How do you?
Yeah, let me bring up a little Word document here and I'll type it out for you. Because that seems, oops. Let me, new document. So when we look at, it's actually any modeling, but logistic. When we look at a null, so first of all, let me start like this. Our summary of risk of diabetes is this. I'm just going to paste this in here as PDF. Don't need it to be that big. I don't know why Jump always comes in with things as like giant. Oh, that was fun. All right, so let's take this. Good Lord. I think my Word has decided it's Friday afternoon, right? So this is my summary of risk of diabetes. So knowing no other information, I would say any given person that is similar to the descriptors that we have, right? That fits in with our population is 27.4% likely to be at high risk of diabetes. So without knowing anything else, if all I know is that we've got 27.4% of people are in the high risk category, if a random person came up to me and said, what's my risk of being in the high risk category? I would say, oh, 27.4%. That's your chance. Does that make sense?
Yes.
Okay. So the question for the model, our null hypothesis here is that the proportion for high risk diabetes, if I can do this, is 27.4%. That's what we know right now, right? That's our status quo, that knowing no other information, this is what it is. There's a statistical way to put this, but we're just gonna play with words right now. And so if I think about the alternative here, variables in this model give me a better, not give me, let's say provide. That's all I'm asking of my whole model test. Am I just going to stick with my proportion of high and low? Or do these variables in this model, is this model going to give me better prediction?
Okay.
Does that make sense?
Yes, that cleared it up a bit for me.
We're going model, no model, right? This is where we are. I know 27.4% of people in my sample for this population are at high risk for developing diabetes. My question is if I know things like their age, gender, BMI, total cholesterol, and glucose, does that get me a better estimate of their likelihood of being in the high risk category? So that's all the model does. And that's what this is. And so I press run and I get my logistic output. The very first question I want to ask or I want to answer is this one. God, why is Word it tries to be so helpful? I don't want it to be helpful. This is my first question that I want to answer to. And this is the whole model test. That is right here. So the very first thing I need to take a look at is the p-value for the whole model test. And my p-value here is very small, right?
Yes.
And so I would choose which of my hypotheses based on this p-value.
You're going to reject the null hypothesis, right?
Yep. And conclude that this model is useful. So that's all we've done so far, right? So we know it's useful. What's the obvious next question? I put in 1, 2, 3, 4, 5 variables into this model. What's the obvious next question? The model's helpful.
Which variables are predictors of high risk of diabetes?
Yay, you get a gold star. So
I
that's
do have a question really quickly before we. The alpha level for logistics, is it always going to be the, what is it, 0.05?
In general, yes. Our alpha level for any statistical analysis is 0.05. Whether it's logistic, linear, contingency table, group means, ANOVA. So it's always interesting having students come through these classes that they think that when we get to a new type of analysis that the interpretation of p-values changes. It does not.
Okay.
So our interpretation remains the same. For varying studies, for pilot studies, for studies with large sample sizes, the investigators may use a different alpha. So they might use 0.01, or they might use 0.001, or they might use 0.10 instead of 0.05. But that's a much deeper conversation than BST 601 allows us to go into.
Okay.
Standard practice is that your alpha is 0.05.
Got it. Thank you.
Right? So compared to an alpha equal to 0.05, right? So that's why when you read manuscripts, you'll always see in the methods section, they'll state what their alpha level is.
Okay.
Always assumed to be 0.05, but people can change it. But it's really clear, like in posters, in abstracts and manuscripts, that you state that so that people know that if you had a p-value of 0.07 and you say it's statistically significant, you can go, wait a second, compared to what? 0.07 is bigger than 0.05. So maybe they used a 0.1. So yes, 0.05. So on to our next question of which variables are predictors of diabetes. And we're going to have several null hypotheses here, right? Is not predictive. So if I can spell and type, it's Friday. I don't know that having a cocktail during this would be helpful. Gender is not predictive, and the thing that we need to put out here right, because it's in the presence of the other variables. We already know gender is not predictive on its own. We already saw that. So then we've got BMI is not, and you could say is not related to, you know, there's lots of different ways, high risk, diabetes. And then again, in the presence of the other predictors. Let's do this, AKA adjusting for. Okay, then we have the same sort of setup here for total cholesterol is not related, and we could say glucose does not predict. These are all the same question. Do you see that? Like, just depending upon what words feel right to you, these are all the same question. So we go down here to, you can use either the parameter estimate p-values or you can use the effect test p-values. It's up to you. You can see that they're almost identical. I tend to go with the effect test because they're the likelihood ratio chi-squares, and that's a better test. These are called walled chi-squares. I have no expectation that you will remember that or need to know why. They rarely disagree, but the likelihood ratio chi-square tests are a better test. So let me just put a little bit of that here. Okay, so for test number 1, that's gender. What is our gender p-value? Oh, I forgot about age. We'll come back to age. What's our gender p-value here?
I'm sorry, I got bad eyes. Like,
okay, it's 0.7.
I can't see that second number.
7641. Okay. Okay. So what's our decision here?
Fail to reject.
Yep. Fail to reject. Gender not related to being high risk for diabetes. Okay. I forgot about age here. Let's put age. Okay, so let's do our second question, which is BMI. What's the BMI p-value for the poor eyes?
0.0001.
Yeah, less than 0.0001. So we will what?
Reject the null hypothesis.
Yep. And we will conclude that BMI is related to being high risk for diabetes. Okay. So we're going to leave it at that for now because we're just going to answer the rest of these. Okay. So for total cholesterol, the p-value equals 0.1170. Again, this is fail to reject, not related, right?
0.1185.
Reject. Yeah, so that's this one. I picked this one because I like the likelihood ratio better.
Okay.
So use the likelihood ratio chi-square. That's what I like better. It's not what I like better, it's actually a better test.
Okay.
Okay, glucose. P-value is what?
0.0085.
Okay, and so we are going to reject. but let me type this correctly, reject H naught, and we are going to conclude that glucose is related. Glucose is predictive. Okay, and then finally for age, it's our first p-value that I had ignored, type equals 0.2775. And so that conclusion then is fail to reject and not related. Okay, so we know that we have
Okay.
these two things, BMI and glucose, are predictive of being high risk of diabetes. What is the obvious next question for that? We know they're related.
How are they related?
Yes. See, you know how to do this, right? How are they related? So let's take a look at that. And glucose. To do that and jump, what I want to ask for here are the odds ratios. The red drop-down arrow at the top. Okay. So normally in a situation where we just had an unadjusted analysis with a continuous measure, we would say, oh, well, we know that the mean BMI for the low risk category is lower than the mean BMI for the high risk category. We report the means. Here we actually want to find out for every 1 unit increase in BMI, how does my likelihood of becoming high risk change, right? Because we're not predicting a continuous value. We're predicting whether or not somebody is low or high risk, right? So we're not giving them a number. We're saying you're more or less likely to be high risk versus low risk of diabetes. So that's the odds ratio. If a variable is not related, then the risk is 1, right? You're equally likely to be low risk or high risk. So gender isn't predictive. So knowing somebody's gender, you know, males to females, they're equally likely to be high risk. Doesn't help me. In BMI, what you get here for our BMI, we want to look at per unit change. We want to look at the per unit change. Whoops. Did something weird. But I think this is where things get tricky, because you have to pay attention to this. So the odds ratio, it is telling me for low risk to high risk. So it's predicting on the likelihood of being low risk, right? Low risk is good. It's predicting the likelihood of being low. And it's predicting on the likelihood of being low because L comes after H in the alphabet. And JUMP does this weird thing where if you have them ordinal, it's trying to predict what gets people in the low risk category. So these have been value ordered. Do you guys want to see how to switch it?
Yes, please.
So if I go back here,
Why do you say A comes before H? How does that matter?
no, I'm going to show you here why. So if I go into risk of diabetes and go into column information, and I go into value ordering, it's having low come before high because it's doing it in reverse alphabetical order. It's stupid. I don't know why it does that. But I want to swap it. I want to look at high risk compared to low risk. So I'm just going to swap it. I value ordered it so that I can get my odds ratios to tell me the probability of being high risk. That's what I'm interested in. So you can change them, and we'll see here, now that I value ordered it, if I go back to my fit model and fit the same model, age, gender, BMI, total cholesterol, and glucose, this is exactly the same as the models we fit before. What you'll find out here is that this is the same p-value. These are all the same p-values. But what you get now when you look at your odds ratios is we're now looking at the odds of being high versus low. Let me pull up my other window. So all of this top part hasn't changed at all because it's the same model. I just flipped the way that I'm predicting. Am I predicting? I was the first one saying, what's the likelihood of being a low risk? And now I'm looking at the likelihood of being high risk. So the variables are still related in exactly the same manner. It's just now giving me a different prediction. And that's okay. Like, that's totally fine. Don't worry about it. You just need to make sure with Logistic that it makes sense to you. And in my case, I think in this case, we're more interested in predicting somebody's risk for being in the high risk category, or the likelihood of them being in high risk. So we'll use this one for the interpretation. And what I can see here is that I have, for my BMI, which was significant, I have an odds ratio of 1.3. And I have a 95% confidence interval, and we'll talk about that in just a second, of 1.2 to 1.4. And for glucose, I have an odds ratio of 1.03. And I have a 95% CI of 1.01 to 1.06. So I've used 2 decimal places on glucose because if I round it, I'm going to get 1.0, 1.0, 1.1. And that's not super informative. So I've got 2 decimal places here. I don't need that for BMI because it doesn't round to 1. This isn't stuff, again, I don't expect you guys are getting much more logistic education here than the rest of the class. But this is good in ways of interpretation, especially for your final exam, which is really a quiz. So ask for odds ratios. So now let's talk about what these mean.
So the glucose of 1.03, what I'm seeing is 1.02. How did you get 1.03?
Right there.
Okay.
It's 1.03.
Okay, unit odd ratio. Okay, we're looking at the range odd ratio.
Yeah, so the range odds ratio is something that I generally ignore. It's saying if you go from the lowest value of glucose all the way to the highest value of glucose, how does your risk change? That's generally not useful. You get crazy values because somebody's not going to go from the lowest BMI to the highest BMI like instantaneously. That's not something you can change, right? Like it doesn't, the range odds ratio isn't very useful. In fact, I'm just going to close it so that we take a look at it. So odds ratios can be really tricky to interpret. In words, 1.3 times more likely to be in high risk category for every 1 unit increase in BMI. So if you think about the X versus Y, as BMI increases, you're more likely to become in the high risk category of diabetes, right? We know that. That makes sense, right? That intuitively makes sense to us. The larger people are, so their BMI gets bigger, they're more likely to become in a high risk category for diabetes. This is just telling us that for every 1 unit increase in BMI, they're 1.3 times more likely to go into high risk. There's a thing in JUMP that I really, really love. And it's again up in this red arrow. I'm going to share this document with you guys. Ask for profiler. I can type. And I'm going to go up here and I am going to ask for this profiler. And I'm going to get this nifty little thing here. I'm going to make it bigger so that you guys can see. Go down here and make it bigger still so we can see. Make this bigger so you can see. This is only for jump because you can't have interactive graphs on paper. But it's going to allow you to see here BMI. So it has picked the mean. Remember the mean BMI was like 26 or something about there. So it's got me at the middle BMI, and it is telling me right now, the middle BMI with all these other variables is saying that there's a 21% chance of being high risk. Watch what happens when I move BMI up and down. Look at that. At the top BMI, they have a 95% probability of being in high risk. As we come back down, we can see. So this is that range odds ratio, right? But nobody goes the whole range. So I can say, okay, let's say I'm 30, right? So I've got it stuck at 30, holding everything else consistent. So for a 48.5-year-old person who is female with a total cholesterol of 189 and a glucose of 91.3, right? Do you see where that is down here? So
Yeah.
Age is at 48.5. They're female. This is where their total cholesterol is, and this is where their glucose is. For a 30 BMI, we're predicting them to have a 43% chance of being high risk. Now let's say I get them to lose weight, right? Because their age isn't going to stay the same, or their age is going to stay basically the same, gender is going to stay the same. What if we can get their BMI down to 25? Now look at their risk. Their chance of being high has gone much lower. So this is what I love about the profiler. It really helps you understand what those odds ratio means. Our odds ratio is telling us as we go from 25 to say 26, that means I'm 1.3 times more likely to be high. That's what our odds ratio tells us. And that's what this line is showing us, right? As we go up and down BMI, our risk of being high changes. That's why I really like profiler. If a glucose, or if it's less than, right? If this is less than 1, then it's telling us it's protective. So if I had an odds ratio of 0.4, it would tell me that for every 1 unit increase, I'm less likely to be high risk because it's less than 1. So glucose is really small because glucose doesn't have a very big range. Like our 1 unit increase in glucose is a small amount. And so you can see the curve is much less steep. Like look at how steep the BMI curve is. So every 1 unit increase is more of a chance of being high risk. Glucose sort of creeps its way up. It's not quite as significant. Males and females, look as I change from female to male, right? Nothing really happens. See how flat that stays? And that's reflected by the fact that we have a really not significant p-value here. Knowing somebody's gender isn't really going to help you change their high risk. Doesn't do anything. Same thing with age. There's not a big change in age either in the high risk. So that's logistic. There's 2 things that you want to report really. One is the odds ratio, right? And then you could say for female age, 48.5 with a total cholesterol and a total cholesterol equal to this and a glucose equal to this. Probability of being high risk equals that. And so you could then pull those numbers from here. Jump in the red drop down here also will output you a grid table. And it'll actually give you a whole bunch of combinations, right? Which is really nice. So if I wanted to look at So this is the smallest n, 19-year-old female, BMI of 18, low cholesterol, low glucose. They're basically going to be low risk. 99% chance that they're low risk. Very small. If I go all the way down to the other end here, you guys are getting way more logistic than everybody else. I'll go all the way down here to somebody who's 79, male, who's obese, high cholesterol. They're 99% likely to be in the high risk category. Okay, questions about logistic?
So on the quiz, there was a question about, not the quiz, but learning check 11. There was a question about dummy variables.
Yeah, skip that.
Those aren't, skip it.
Yeah, okay. You can answer it, but you're not going to get, everybody gets a free point for that one.
Okay. And then I guess my only other question is, it was extremely helpful, like when we did ANOVA and the t-test, when you broke it down for the midterm, like which variables determine which test you run. Is there any way that we could do that for, I guess, the multiple, whatever we just did in module 10?
Yeah, so when you do group means, right, that's an F test when you have multiple groups. Right? So when you're doing linear regression, it's still an F test. Like when you have a continuous outcome, it's still an F test. When you have a categorical outcome, it's always a chi-square test. So for logistic and linear regression, it's going to follow the same. So if I have, right, if I have fit y by x and I have categorical y and categorical x, that's contingency. I can spell contingency, and that is a chi-square test, right?
Right.
Okay. If I have a categorical, if I have a continuous y and a categorical x, that's group means. That's a T or F. An F test for multiple means, that's ANOVA, right?
Okay.
So now, if I have a categorical y and multiple x variables, that's logistic. Logistic. Still chi-square. Okay, and if I have a continuous y and multiple x variables, linear regression. The whole model is an F test, right? The whole model. That's our, is this model useful or not? And that's followed up with t-test for each variable. This logistics is all chi-square.
Okay.
Is that what you meant?
Yes.
Okay.
Thank you.
Absolutely.
So when you say single mean test, there was the one you said about single mean test in the last exam. Is it the same thing as ordinary t-test?
So group means t-test?
No, not group. There's the one that you said single mean t-test.
There's no single mean. So like if you're comparing a mean to a historical mean, that's a t-test. If you have two groups for x and a continuous y, two groups for x, like male, female versus BMI, that's a t-test. If you have three groups, like white, black, and other race, that's an F test.
Okay.
When you go to linear regression, the whole model test, is this model useful or not useful, is an F test. When I change to, here, I can just show you. All right, so we've got, I'm just gonna do a stupid analysis here just so you can see. So if I go fit model and I wanna try to predict total cholesterol, right? That's a least squares regression. It's linear regression. Let's say I throw in age and I throw in gender and I press run. I want my whole model test. Analysis of variance test, that's an F test. That's my whole model test for linear regression. This would tell me this model is useful, right? Significant p-value, this model is useful. My next question, which variables are useful? Those are down here, those are t-tests. It's doing what we did for correlation. So this variable versus that variable, is it useful? It's a t-test on the slope. So it compares it to 0. So in this case, age is useful in predicting total cholesterol, gender is not. It is very literally an identical setup. Whole model test, individual variables. The test that you're using, whether it's a chi-square test or a t-test, doesn't actually matter because we look at this, right? We look at our p-values. So you don't need to be super concerned that it's a t-test. You just need to look at the p-value. Or you don't need to be super concerned that it's a chi-square test. I mean, it's good to know it, obviously. But we don't report, if you go through this paper that I've given you to look at for the final exam, which really, by the way, is a quiz. Don't freak yourself out about it. I don't report the chi-square values anywhere. I don't report the F-test values anywhere. It's just p-values. Because it doesn't mean anything unless, like this F-test doesn't mean anything unless I report the degrees of freedom. And then most people don't know what that means anyway. So just report your p-values. Okay?
Okay.
Thank you.
Absolutely.
Okay, continue. Let me get my list.
So what I'm going to do for you guys is we're nearing the 5 o'clock hour, and I've been talking for 5 hours. Is I am going to let this video process. It'll take a while, so it won't be till tonight, but I'll put it up on YouTube. And since this is so helpful, I'm actually going to post it for the whole class so that everybody can see it if they want, if that's okay with you guys.
Absolutely.
Okay, so I'll get you this logistic demo document and I'll upload this dummy data, this stupid data, this sample data, and the video, and I'll post that on Canvas for everyone. This is way more than you guys need for this class, but will come in handy in the future.
So my own question was not, my own question was on chi-square. The last video you uploaded for us, the one you said we did on cholesterol, the learning check.
Yeah, the learning check.
Yes, so the one we did on total cholesterol 500 and the total group cholesterol.
Yep.
So when I was doing it with, I'm using Windows 7. So when I was doing it, the area where we are doing a formula, so my own did not do like.
Oh, your formula didn't work?
Yeah, it didn't work. I don't know how. Is it because of my window or because of anything? I don't know.
Yeah, so to do that,
if you don't mind, I can share my screen to show you what I mean.
Yeah, absolutely. So Diamond, if you want to sign off, you can. We're just going to have a quick jump discussion about Agatha's jump. She's on mute. Okay, let me make you a co-host. Yeah, sure, no problem.
I appreciate it. Thank
Absolutely.
You.
Have a good weekend.
You too.
Okay, Agatha, I just made you a co-host.
Okay.
And you can now share your screen and we'll see what you got.
Are you seeing my screen?
It usually takes a second, so did you do share?
Yes, let me cancel it and redo it again. Sorry, my daughter is in Spain. They are doing their e-learning. You may be hearing her voice.
It's just super slow.
Yeah.
Yeah, you're gonna have to unfortunately get rid of your Windows 7 machine soon.
Yeah, I know.
Okay,
Are
so
you seeing
pull
my
up,
screen now?
yeah, pull up jump and let's see what your formula looks like. Oh, you've tried lots of times.
Yeah.
All right, so go into that first one. Let's see what your first one looks like.
So, okay, for this one or this one?
Whichever one.
Okay, let me go for this one.
Okay.
So,
Go into column information.
yeah, this one.
Yeah, there we go. Okay, so do edit formula. I can tell you exactly what the problem is. Go click on edit formula right there. Yep. Okay, you see how your desirable doesn't have quotes around it?
Don't mind this one. I entered this one by myself.
No. So let's first of all just take, oh yeah, so recoded total cholesterol. Where is that variable? Where's your cholesterol variable?
The 500 cholesterol?
Yeah, so it's,
That's this one.
right, so what you want to do is actually use the raw cholesterol value. So, or the recode's fine. That's what it is, recoded 500, so that's fine. Okay, see how where you've got the arrow? So this is the recoded total cholesterol 500 less than 200. Then I want it to say desirable. You need quotes around your desirable. So click on the word desirable.
This one?
Yep.
Can I do it again so that let me just abandon this one so that you.
Oh, no, we're gonna fix it right here. We're gonna fix it here. Click on desirable.
Here?
Yep, click there. Now press delete. Now do a quote, just one, just do your starting like you're starting a quote.
I didn't get that. What do you mean by a quote?
I mean by a quote, I mean, you know, if you put quotes, yep, like that. Now type the word desirable.
Sorry, looks like I did too.
Just type, no, okay. You went too fast. So press escape, get yourself out. Press escape, we're starting over. Okay, click on that little blue total then clause again.
Here?
Type your quote. Now type the word desirable. See how it fits itself in the middle? Now just press enter. Ta-da! Okay, click on borderline. Press delete. Type your quote. Type borderline. Press enter. Click on high. Press delete. Type your quote. Type high and press enter. Now press apply. You want to apply this formula. Oh my God, you see magic behind it? What just happened?
No.
See down here underneath, you can see the word desirable. So press OK. Just press OK. Press OK. Look. Ta-da!
Where are you looking at?
See your
Okay,
total cholesterol group? Yeah, look at it. It's there.
Okay.
It's because you didn't have quotes. It's a character variable.
Mm-hmm.
So you have to tell jump with those quotes that it's a character in the formula column.
Can I show you something again? Okay, maybe this one you say is also, but let me check. Let me be sure. Like, if I want to use this one for example, because I know I did this.
Again, you don't have the desirables not in quotes here. Like that formula is just wrong.
Can I do a total new one so that I will make sure that I get it right?
Yep. So just close out of that, do a new column. column information. Okay, so first of all, make the data type character. So that data type, the data type right now reads numeric. Make it character. Click on the little arrow next to numeric. Do you see the word data type?
Okay, here.
Yep,
Okay.
so click there and make it character.
Okay, character.
Yep. Okay, so now under column properties, you want to do a formula.
Mm-hmm.
It's all the way up the top.
Mm-hmm.
And now I want to edit the formula. Okay, so start with conditional. There you go. If.
So I'll click on here.
Yeah, go all the way down and select your recoded cholesterol. Yep. Okay, then greater than, right? That's under comparison.
Mm-hmm. Here.
No, so you want to go over to the
comparison. Yes.
Mm-hmm. Do greater than, or less than, sorry, less than 200. Click on the then clause, type your quote.
Okay. I'll first type my quotes.
Yep, first type your quote and then type in desirable.
Okay.
You don't need to enter in the second quote because you see Jump does it automatically when you just type that first one. And then press OK. And then use your little caret up at the top there and click that twice. Yep. And now you want to put your recoded, you want to go into your comparison. So click that little EXPR. Nope. First you got to be in the right little.
Okay, here, yeah.
Yep, click there. And now go to comparison. Well, you double clicked. Just press escape.
Sorry.
Just press escape, it'll get you out of there. Now go to comparison. And now you want it to be one of the ones at the bottom. You want it to be greater than or equal to 200, but less than, yep. And then type your two. You got it?
Let me be sure.
Okay.
So I will click on here, right?
Yep. No, but that's your 200. Remember, that's your lower that bound. You want to type your number in there.
Okay, 200.
Yep. And then in the middle one, click on that. And that's yep, that's that one.
It doesn't come in.
No, but you can, so click on the middle again. Click on the middle one and then go, yep, click there.
Mm-hmm.
And then go back over to your variable name over in the middle and click it again.
This side?
Yep, that one. Click your recoded cholesterol 500.
Here.
Yep, click right there.
Again? Okay.
Yep,
Yeah.
click it again.
Ah.
Yeah, and then click on your right side box and whatever value that was. I don't remember what the...
240, right?
Yeah, sure. I don't remember it off the top of my head.
Yeah.
Right, and then in your then clause...
Okay.
Quote, moderate, or whatever the middle is. Borderline.
Yeah, borderline.
Yeah. And then high. Quote, HIGH. Enter. Now press apply and watch what happens on your data in the background. There they are. Ta-da. And then you
click OK.
Yep, okay and okay, and there you go. Now you got it.
Wow.
Yeah, fancy, huh?
Yes.
Yeah, that quote thing is really important.
Yeah, because if you didn't tell me now to do
quote.
So to do quotes, I wouldn't have known it. I would have. That was what I did, and it took me the whole day. I didn't do anything. Only trying to get it.
Oh, it's good to figure things out on your own, but it's also good to recognize when you hit a roadblock, and this was a roadblock. So that's fine. So now you know how to do it.
Yes.
Okay,
Thank
fantastic.
You so much.
Absolutely. I'm gonna sign off. I'm gonna have a cocktail.
Thank you.
Have a good weekend.
You send this recorded version, right?
Yeah, it's gonna take a while. It'll be later tonight before it gets posted.
So this part I did now, is it gonna be there?
I'll send it to you.
Okay.
Okay.
Yeah, because I need this particular one I did now.
Yeah, it'll probably take like an hour or so before this like renders, and then I gotta upload it to YouTube, and that takes a while.
Okay.
Okay?
Thank you.
All right, have a good weekend.